Hello! In this presentation I will talk about the role of smart vision sensors in energy-efficient computer vision at the edge. I will start by introducing some of the concepts that will be used in this presentation. So, typically, when we want to execute a neural network-based solution, we rely on very powerful hardware, such as a server or a workstation computer, requiring thousands of watts of power. We can also run these solutions locally, for example, on a personal computer or a small single-board computer. Think Raspberry Pi, for example. This cuts the power consumption to 10 to 100 watts and is known as edge processing, as the processing is carried out on the edge device. We can also achieve even lower power consumption by going down to Internet of Things devices, usually powered by very low power microcontrollers, requiring less than 1 watt of power. And these are usually contained in, for example, wearables or smart devices or smart vehicles. And running neural networks on these devices gives rise to what's called as TinyML or tiny machine learning. This brings a lot of advantages to the table. For example, in terms of privacy. Running a network locally on these devices allows for what's known as a privacy by design application, as an image, for example, never needs to leave the device and we don't have to send an image on the network for it to be processed by a cloud server, but we can execute the neural network inference locally and then just send higher level information to the network. We also have great advantages in terms of power consumption. As I said before, many of these platforms require less than 1 watt to run, and because of this, they can be powered, for example, by a small solar panel. We also have a very good advantage in terms of bandwidth usage. We reduce the amount of data that needs to be transferred to the network by some orders of magnitudes by performing edge processing. As I said before, we don't have to send a full video stream to a cloud server, but we can just send the high-level information that is given by a network running on one of these edge devices. We also have some drawbacks, obviously. We cannot run huge state-of-the-art neural network approaches on these devices, particularly due to the constrained environment that these networks need to run. In fact, the biggest challenge of TinyML is dealing with the computational resources of these devices. If we consider, for example, a workstation, we can usually make use of tens to hundreds of gigabytes of RAM, terabytes of storage, and hundreds of billions of operations per second. When we start running the models locally on, for example, a personal computer or even a single-board computer, we cut these capabilities by a factor of 10 usually. So the networks need to be smaller to run on these devices. And in particular, the greatest challenge comes from running these networks on microcontroller units, where the computational capabilities are cut at a factor of 10,000. We usually can only rely, for example, on hundreds of kilobytes of RAM and some kilobytes or megabytes of storage, and we can only carry out some millions of operations per second, which is, as I said, orders of magnitudes lower than what is possible on higher level hardware. There are some solutions in order to be able to run neural networks on these devices. The most common ones rely on the network size reduction. For example, employing distillation or pruning or quantization of the network weights. So, distillation refers to the process of having a larger network teaching a smaller network the same task. Pruning relies on removing non-necessary weights from the network, and quantizations reduces the number of bits, for example, from 32 to 8 for each of the weight of the network. We can also rely on some optimized neural network architectures that are designed from the ground up to be able to run on these devices. One example is the finite family that we will use in the course of this research. These are, as I said, networks that are designed in order to minimize the hardware resources in order to run on these very small devices. And most importantly, we can use, for example, smarter sensors. So sensors that can give us a simpler information to analyze, leading to a simpler problem to solve for these networks, leading to the capability of using a very small network. I will talk a bit about the architecture that we are using first, and as I mentioned, we are relying on the finite family of networks. Finets are very nice in our case, as they allow us to tune the RAM and storage and operations needed by the network in order to adapt the network to many different devices. In our experiments, we will use an object detector that is generated by coupling a finite network to a YOLO object detector. And, as I said before, we will study the relation of this network coupled with different smart vision sensors. We defined a smart vision sensor as an image sensor that implies some form of in-sensor processing in order to provide a higher level representation of the image. For example, we can consider sensors running an on-device background removal step or motion detection, for example. There are a lot of different types of smart vision sensors, and for this study we considered 20 different approaches. We start by analyzing the original image where the sensor is acting. We can have mainly three main outputs. We have sensors giving an RGB output, so three different channels for red, green and blue. We can have channels with a single output, so a grayscale image. And then we can have sensors with no image output, which only output the motion bitmap. The different sensors can then employ very different approaches for background subtraction. For example, we start from a very simple approach, which is frame difference, where the sensor just captures two subsequent frames and computes the pixel by pixel difference between intensity levels of the different frames. And this difference is then thresholded, and where this difference is higher than a set threshold, we identify that pixel as a rapid changing pixel or as movement. We then have more complex approaches, such as the ones based on a k-nearest neighbor or a mixture of Gaussian's background removal techniques. Whatever the algorithm is that we are using in order to generate a motion bitmap, we then have different ways in order to provide this data to the network. In this study, we considered two different ways of merging the motion data together with the original image. We have what we identify as merging, so adding the motion bitmap data as an additional channel on top of the original image. So for example, here we can see RGB images which have three channels and then a fourth channel which is this motion bitmap. Or for grayscale images, again, we have an output that is composed of two channels, and here we can see the two different channels, the original grayscale image is represented here in the purple channel, and then the motion bitmap is represented again in the green channel. Together with this merging methodology, we also employed a masking methodology. So we consider the output as the pixel-wise product between the original image and the motion bitmap. This gives us an output that is composed of the same number of channels as the original image, so 3 for RGB data and 1 for grayscale data. And the output is all 0 except where motion is detected. We also use only the generated motion bitmaps in order to train these networks, in order to see if even this input type is sufficient. As I said before, we are interested in object detection. So, object detection is the task of locating different targets in a given frame. For example, here we can see that our target are people, and the network is successfully capable of identifying the location of the different people in frame. The performance of an object detector is usually measured in terms of mean average precision, which is the average across all different classes of the precision. Precision is simply the area under the precision and the recall curve, or in mathematical terms, the integral from 0 to 1 of this curve. I will talk a bit about the data that we used for these experiments. We relied on 3 publicly available datasets, which are MOT15, MOT17, and Oxford Town Center. We only considered the sequences that are captured from a fixed camera from these datasets, and this is because these are the only sequences where we can reliably employ our background subtraction. We employ some form of image augmentation by getting 5 random crops from each of the input frames, and these random crops are randomly zoomed in and cover between 10 to 50% of the region of the original image. All in all, we end up with around 11,000 crops containing 55,000 bounding boxes. On this data, we will run 2 different experiments. The first experiment is targeted at understanding if the smart vision sensors actually help for an object detection task. We want to understand if the additional information provided by this kind of sensors actually help our task, and if this allows us to make the network smaller, as we are relying on a smaller number of input channels. Also, and most importantly, we want to understand what is the best input type, so what is the best output that an ideal smart vision sensor can give us in order to achieve the highest performance. So, we trained an object detector on each of the 20 input types separately, and then we evaluated the performance of this detector based on the operation count and mean average precision, as I said before. Here you can see some of the selected results from this first experiment. You can see, for example, the first line is the baseline object detection task, where we give our network a simple 3-channel RGB image, and we evaluate the mean average precision that we achieve from this process. We can see from this table that a 2-channel input comprised of a grayscale image coupled with the motion bitmap actually shows higher results in terms of mean average precision, and this is by a significant margin. For example, here we can see that the grayscale and motion bitmap input allows us to achieve around 20% higher mean average precision with respect to the standard RGB data. And also, this allows us to achieve smaller networks, As I said before, we are only relying on fewer input channels, so we have fewer ways in the network at the beginning stage, and this gives us fewer computations for the input stage of the network. We can also see that this increase in performance is almost independent from the background subtraction algorithm that we are using. Here we can see how a naive frame difference approach just gives us a 0.1% lower mean average precision compared to the highest performing KNN background subtractor. So we can understand that giving the network some temporal data, no matter if it is obtained with a very complex approach or with simple frame difference, actually really helps the network to perform its object detection task. And in this GIF, I highlighted what the best performing output of a smart vision sensor looks like. As I said before, these are images composed of our grayscale data coupled with the motion bitmap on a second channel. Again, you can see the background grayscale image in purple and the overlaid motion bitmap in green. We then wanted to understand if this motion bitmap is actually considered by the network in order to influence its output. In order to do this, we computed the different channel importance that is given by the input stage of the network to all the different input channels. This means that we analyzed the weights of our input stage in order to understand which of the input channels had a greater effect on the output of the network. Here you can see two plots regarding the RGB and the grayscale with motion bitmap data. In both plots, you can see how the alpha channel, which is our additional motion bitmap channel, influences the output of the network far more than all the other channels considered by the network. This is especially obvious in the case of the RGB image, where the alpha channel determines more than 80% of the output of the network. But even in the case of the grayscale and the motion bitmap data, which is the best performing input, as we said before, we can see that more than 70% of the output is determined only by the motion bitmap channel. Actually, this proves that the additional information coming from this kind of sensors really helps in our object detection task. We could guess from this that using only the alpha channel for our network would be enough. But as we can see in this table, using only the motion bitmap gives us greatly reduced performance. This is because when we use only a motion bitmap input, when targets are close to one another, the network will only predict one bounding box compounding all the different targets. The additional data coming from the original image, when we merge it with the motion bitmap, allows the network to differentiate between different targets. The second experiment that we carried out was targeted at understanding if we can use the data coming from a smart vision sensor in order to allow for very small networks, smaller than what is possible by using a standard RGB image. We want to understand if the simpler input type provided by this kind of sensors can allow better performance on very small networks. And as I said, we want to understand if we can go lower than what is possible relying only on RGB images. For this experiment, we trained different complexity finits for each of the input types. In particular, we targeted the networks at around 3 million operations, 6 million operations, and 9 million operations, which is a good range for low-power microcontrollers. In this experiment, we only considered the k-nearest neighbor-based background subtraction algorithm, as this showed the best performance compared to the other approaches in the first experiment. Again, we will evaluate networks based on operation count and MAP. This is a plot of the performance of the different networks, changing the input type and with different complexities. As we can see, again, the simple grayscale input compounded with the motion bitmap outperforms all the other input types in the considered complexity range. We can also see how, nearing the 10 million operations, the RGB compounded with the motion bitmap starts getting very close to the grayscale and motion bitmap input. We can imagine that given a larger network requiring more operations, this more complex input will actually outperform the two-channel input that was the best performing before, as an RGB image compounded with the motion bitmap presents a lot richer information than what is possible with just a single channel. We can also see, as we've seen before, how the simple motion bitmaps alone do not lead to significantly good performance and are actually not really usable by themselves. This is probably due to how we have set up our dataset, where there are actually multiple people per frame, and so we have overlapping objects that the network needs to distinguish between one another in order to achieve good performance. So relying on only a single channel black or white image does not seem to produce good results. So, in conclusion, in this work, we have seen how using a smart vision sensor can allow for a significant increase in the performance of an object detector. And in particular, on average, we can achieve a 10% increase in MAP by adding the motion bitmap as an additional input channel to our neural network. One curious fact that we found out was that any kind of background removal strategy, be it a very complex mixture of Gaussian-based algorithm or a very simple thresholded frame difference approach, brings very great performance improvement in object detection. As I said before, this is probably due to the fact that any one of these approaches brings an additional temporal dimension to the input data that the network can exploit for its predictions. One curious fact that we found out is that, given our dataset, the standard RGB color space that is used in order to train object detectors proved actually to be the worst kind of input possible, leading to the most degraded performance with respect to all other input types. Thanks for your attention. If there are any questions,